Now that we have seen that we can still measure relatively the size of infinite sets, now we come back to the question of measuring subsets of Rn, subsets of Rn, and we will see that the problem of measure starts here. Now, whenever we are trying to measure subsets of Rn, they can be finite sets or infinite sets. If we simply use the cardinality to be infinity, then we only get infinite values and we cannot do any arithmetic with it, so it's not very useful. If we use equinumerosity, so if we use the concept of equinumerosity, if we use the concept of equinumerosity, then one can still have an idea of the relative size of subsets of Rn. So suppose that n equal to 1, and we take two sets 0 1 and 0 2. Now there is an injection f from 0 1 to 0 2, but there is, one can easily also produce a bijection simply by taking x to 2x. So we see that these two subsets of R are equinumerous. Okay, they are equinumerous. But our geometrical intuition says that the set 0 1 is half the size of the set 0 2 in terms of length. So if we want to have our geometrical intuition conform with the idea of equinumerosity, then it's no good, because it says that both these sets are of the same size. In fact, one can even have, for any epsilon greater than 0, for any epsilon greater than 0, the sets 0 epsilon and this set 0 2, for example, they are also equinumerous. So you can take epsilon to be as small as possible and still they are equinumerous. So it not only violates our geometric intuition, but it gives you a sort of contradictory intuition that as you can have as small a set as possible, 0 epsilon, but it will still be of the same size of 0 2. So this violates our geometric intuition, and so we are trying to search for a way of assigning numerical values to subsets of Rn which will conform to the geometrical intuition that we have in terms of length, area or volume, etc. But such a thing is not possible was shown by a theorem of Banach and Tarski. This is the famous Banach-Tarski paradox. And this states that there exists a decomposition of the two sphere. So the sphere in R3 of the two sphere into finitely many pieces, which can be rearranged to form two spheres of the same size as the original one, which means that we can break apart something as the size of a peanut or a pea, and we can reassemble it into many pieces of the same size, and we can repeat this over and over again, and we can produce by taking again the rearrangements to produce something at the size of the whole earth. So this is a kind of a paradox, but this paradox uses the axiom of choice. So it uses the axiom of choice in a fundamental way. So what is the axiom of choice? Let me recall. The axiom of choice. So the axiom of choice says that given a collection of non-empty disjoint sets, this collection is denoted by this calligraphic A, there exists a set C such that C is a subset of the union of all the sets in this collection A, and the cardinality of C intersection A is 1 for each A in A. So one can think of it as choosing one element from each of these constituent sets, small this Latin A, and we can form a new set C by taking arbitrarily many such choices, and this is why it's called the axiom of choice. Now, a consequence of the axiom of choice for infinite sets, we have seen that if there is a bijection between a set and a proper subset of itself, then it is infinite. A consequence of the axiom of choice is given by the following theorem, that A is an infinite set if and only if there is a bijection between A and some proper subset of itself. So this is a consequence of the axiom of choice, which characterizes the infinite set as the bijective correspondence between A and some proper subset of itself. Now coming back to the Banach-Tarski paradox, it says that you can decompose the unit sphere into finitely many pieces and reassemble them to give two copies of the same original sphere, and this violates our principle of cardinality. So the Banach-Tarski paradox violates the principle of finite additivity. The principle of finite additivity, and it is something like saying that you have a cup of water and you can break it, you can divide this cup of water into many pieces and reassemble it, and you will get a whole gallon of water. So that is not possible, and it leads to this paradox. So this is why it is important to have a concept of what are measurable sets and what are non-measurable sets. So the non-measurable sets will fail to have this finite additivity property, and the measurable sets will be the ones which are well behaved in terms of additivities, not only finite additivity but even countable additivity, as we will see in our next lectures. So if we want to follow our geometric intuitions for subsets of Rn, so geometric intuition for subsets of Rn, then any way to assign a numerical value, so for any subset of Rn, I want to assign a numerical value, finite numerical value if possible, which corresponds to our geometrical intuitions, to geometric intuitions. So what are the geometric intuitions that we have? So first one is the finite additivity, is that if you take two disjoint subsets of Rn, if E and F are subsets of Rn which are disjoint, then the measure, which I denote here by M, which is the numerical assignment of this union of these two disjoint sets, should be the measure, the sum of the measures of these two things, E and F. So in terms of length or area or volume, we also expect that if you take two subsets of Rn of finite volume which are disjoint, then the union, the volume of the union will be the sum of the respective volumes. So this is finite additivity. The second one also is some geometric intuition, which is invariance under rotations, translations and reflections, which means that if you have some subset E of Rn, and if you rotate it, so this is our original set and you have rotated it by some angle theta, then the area should not change. Area is invariant under rotations. Similarly for translations and reflections. So the question is whether one can assign a numerical value ME to any subset E of Rn such that both these conditions 1 and 2 of finite additivity and invariance under rotations, translations and reflections are satisfied. And the answer is in the negative. Answer is a no, and this is due to a theorem of Banach and Tarski, and it's also known as the Banach-Tarski paradox, which says that given a ball B in R3, there exists, so this is a solid ball, there exists a decomposition of B into finitely many pieces, such that they can be reassembled. So these finitely many pieces can be reassembled to produce two disjoint copies of the ball B. So this will lead to the violation of our finite additivity property. Now let's see how the Banach-Tarski paradox leads to the violation of finite additivity that we described before. So first of all, for any E, a subset of Rn, we denote by mu E. This is a value in 0 infinity, which is the numerical assignment of the measure of E. Now the Banach-Tarski paradox says that the ball B can be written as the disjoint union of a finite number of sets EI, I from 1 to n, but also that there exists B1 union disjoint union B2, which can also be written as a finite union Fi, I from 1 to n, and each Bi is a copy of the unit ball B. So if we try to apply finite additivity, we quickly get a contradiction. Here, by reassembling the EI to form B1 and B1 union B2, we mean that these Fi's have the same measure as the EI's for I equal to 1 to up to n. So Fi's can be formed, for example, by a sequence of rotations, translations and reflections of the EI, and therefore since we have assumed that the measure remains invariant, mu of Fi should be equal to mu of EI. Now we have from, let's call this equation 1 and let's call this equation 2. So from equation 1 we have that the mu of the ball B, the measure of the ball B, is the sum of the measure of the EI's, I equal to 1 to n. On the other hand, the measure of B1 union B2 is equal to I equal to 1 to n mu of Fi, but note that because B1 and B2 are just copies of B, then this is equal to 2 times the measure of B, but on the right hand side each mu of Fi is equal to the mu of EI from our invariance due to rotations, reflections and translations. Therefore this is equal to I equal to 1 to n mu of EI, which is mu of B. So you get 2 mu B equals mu B. Therefore either mu B should be 0 or it should be infinite. Therefore we get a violation for the finite additivity property as a consequence of the Banach-Tarski paradox. Now the Banach-Tarski paradox uses the axiom of choice, and this says that, and so as a consequence of the axiom of choice, we have to separate subsets of Rn. We have to separate subsets of Rn into 2 categories. One is measurable subsets and another is non-measurable subsets. So the measurable subsets will follow our geometric intuitions 1 and 2. So both finite additivity as well as invariance under translations, rotations and reflections, but these sets will not follow both those conditions, will not follow 1 and 2. So the whole idea of measure theory is to study these measurable sets which follow certain geometric intuitions, and we try to build up a theory which is consistent with our usual axioms of set theory as well as the axiom of choice. So we will see in the next lecture how we can start to assign numerical values to subsets of Rn which follow both our finite additivity rule as well as invariance under rotations, translations and reflections.